This is lesson 6.1. The objective of this lesson is to teach you what equilibrium is, how to set up an equilibrium constant, and what that equilibrium constant even means in terms of an equilibrium reaction. So, the first thing you need to know is the definition of equilibrium. I know this is a lot that's being displayed, but I'm gonna walk you through it. So, chemical equilibrium, as it says here, is a reversible reaction. What that means is that you're going to have a mixture of both reactants and products. You're going to make some products, and then some of these products are going to be converted back into reactants. And eventually, you're going to reach an equilibrium, meaning that the concentrations of each are no longer going to change. So let's say you have a bunch of reactants and no product. You're going to start to make some product, and then some of this product goes back to the reactants until the concentrations become constant. They no longer change with time. What these double arrows mean is that the rates are the same, not the concentration. So the concentration will remain constant, but not the amount. So you could be making product at a constant rate. You could have the same concentration over time, but that doesn't necessarily mean that this concentration of product is going to equal this concentration of reactant. Okay, it's not what equilibrium is. It just means that you're making product and you're making reactant at the same rate. That's it. In order for equilibrium to occur, the reaction needs to take place in a closed system. So there cannot be any openings. Nothing can move to the surrounding. Okay? It needs to be a closed system. Equilibrium is also a dynamic process, meaning that once equilibrium is achieved, that doesn't mean that the reaction is going to stop. Meaning that it is not static. Products and reactants are constantly being made at equal rates, not in equal amounts. Okay, the rates are the same, not the amount. Okay, so the concentration that you're making products is not equal to the concentration of reactants. Only the rate is the same. And this slide basically explains what I just said in a very, very clear way. But before I talk about this, I want you to pause this podcast, and I want you to stare at these graphs and answer the question that's presented in this figure. So it says, what can you infer from these graphs? At equilibrium, is the ratio of NO2 to N2O4 less than, greater than, or equal to 0? I want you to look at the y-axis. Both of these are with respect to time. Tell me, write down or mentally brainstorm what you think this figure is trying to tell us. Pause. Okay, now that you are back and you thought about this, I want you to look here at this left graph. So what this graph is showing us is that we are starting off with a lot of N2O4. So if you look at this equation right here, we are starting with a lot of N2O4. So this is N2O4. You have a high concentration of it at time equals 0. So that means you're starting off with a bunch of reactant. And we have no product. Okay, so over time the concentration of reactant goes down, and as the N2O4 is being consumed, you are making more product. You see that? You're making more product as this guy goes down. But eventually, the concentrations become constant. See that? They're constant. They don't change anymore. It doesn't mean that they're the same. Look, the concentrations are different. The concentrations are different. But eventually, the concentration becomes constant here. So at equilibrium, yes, you do have constant NO2 and constant N2O4, meaning that the rates are the same, but the concentration is different. Okay. And if you look at this graph, it's comparing the rate. So if you see, you have a decrease in the rate of N2O4, which is expected because we're making less of it, and the rate is increasing for NO2. But if you look here, eventually they clash, and that's showing us that the rates become the same at equilibrium. So again, the rates are the same, but the concentrations are different here, yet constant. So you need to remember that. Okay, now that you had time to look over it, there's a few things you need to know. Here in this equation, we see that there's 3 moles of N2. I'm sorry, 3 moles of H2. And if you look at this graph, we could see that we're starting off with a lot of reactants. So we're starting off with 3 times, and if you look at this mole, it's 3, meaning there's 3 times more H2 than N2. So we do start off with some N2, see, N2, and we start with no product. Once the equilibrium reaction begins, you consume 3 times the amount of H2, and you consume some N2, and then you make some product. Once equilibrium is achieved, meaning that the concentration becomes constant here, here, and here, we can see that the concentrations are not the same, but they are constant, and the rates are the same. We could assume the rates are the same, even though there's no graph here. So that's how you read this graph. And then let's say the opposite were true. Let's say we had none of this. We had no N2, we had no H2. All we do is we throw the NH3 into a chamber. So here we see NH3 is what we start with, and we start with no reactants in this case. And it's the same idea. So you're going to consume the NH3, the product, and then you're going to make reactant over time. And again, because there's more moles of H2, you should expect there to be more H2 being produced. And at equilibrium, these concentrations become constant, and again, they're not the same. What this slide is basically saying, it's not saying too much, but what it's basically saying is that sometimes we're going to start with a lot of A or only A, and then you're going to make a lot of B. So when it says that the reaction is leaning to the right, we usually write this big arrow here. That shows that we're making a lot of B, okay? And we're not making as much A anymore. The opposite is true as well. So let's say you have a lot of B, then the reaction is going to lean to the left. So you're going to make more A and you're going to make less B in order to achieve equilibrium. So again, this doesn't mean the concentrations are the same. It just means you're making each at the same rate, and the concentrations become constant over time. So if you look at this picture, we start off with only this colorless substance, and once the reaction starts, you start to make some product, and some of that product is then turned back into reactant, and you start to see a little bit of both of the molecules. So this, for example, right here, this colorless substance is N2O4. So look at the molecules. Okay, N2O4 looks like this, and then it gets converted, it gets decomposed into 2 moles of NO2. So they're smaller. See there, they're smaller. These guys get converted to these guys. And then at equilibrium, we start to see a big mixture of the two. So when equilibrium is achieved, the rates become the same. So you start to see a mixture of both. It doesn't mean they're both equal. It doesn't mean these guys are equal to these guys. It just means you're making them both at the same rate. So that's just an application. So that was the theory. Now I'm going to talk about how to calculate the constant. So there's a relationship. So we look back, there's a relationship between the products and the reactants. So the way we mathematically describe this relationship is through a constant. And this constant is called the equilibrium constant, which can be Kc. So the K is the equilibrium constant, but sometimes we put a little c at the bottom. And what that means is that we're expressing this constant in terms of its concentration. Or we could express the constant, the relationship, based on their pressure, the relationship in terms of pressure. So let's say we have this generic equation right here. We have moles of A, and then we have the substance, and then we have another substance, which is the moles of B, and then you have substance B, okay? And during the reaction, you're gonna make a certain moles of D and certain moles of E, with again the moles in the front. So the way the equilibrium constant is set up is we always put the products on top and the reactants at the bottom. So for example, we're gonna put Kc, and again that's equilibrium expressed by concentration, and then we're gonna put the concentration of this substance. The first one we see here is D, so we're gonna put a little bracket because that represents concentration, and then we're gonna put the name of the substance here, and then we're gonna close the bracket because that's the concentration of D. But we also have to consider the moles. So if there's 2 moles, let's say there's 2 moles of D, then we have to raise the concentration by the power of D, because that's how much it's going to increase. The concentration is going to change. It's going to change by a factor of 2. So we put whatever this D is, this little d is, whatever the moles is, we put it on top as a power, and we multiply. I know it says add here, don't get confused, but it's multiply. When we find a constant, we multiply it so that all the products are multiplied and all the reactants are divided. And so we're gonna multiply that by the concentration of E to the power of the moles. Oops, let me get rid of that. And you're gonna divide that by A, power of the concentration of A to the power of little a, times big B to the power of its coefficient, or its mole. So, and again, you have to remember that concentration is in moles per liter. So if they ever give you moles and they say, oh, you have this many moles of A, this many moles of B, this many moles of D, this many moles of E, and then they say, and all of these gases are found in they're found in a 2-liter chamber, like there's 2 liters in that closed system, then you need to divide those moles by that volume, because you need it in this format, in the form of molarity. Okay, so that might have been a little confusing, so of course we're gonna do examples. So if you look here, it says that you could also set this up in terms of pressure. So instead of putting brackets, we could put parentheses, so the pressure of D to that power of the coefficient times the pressure of E times the power of that coefficient divided by the pressure of A to the power of that coefficient to the pressure of B to the power of that coefficient. It's the same thing, we're just expressing it based on pressure. Okay, so I'm going to do the first three examples. So the first, or how about I do the first two and then you try the third one. So it says here, write the equilibrium expression for these three reactions. So the first thing we need to do is we need to set it up. So I'm going to do the first one. So K is equal to, you need to specify whether it's concentration or pressure. I'm going to do it based on concentration. So we always start with the products. Don't start with reactants. So product, I'm going to do the concentration of O2. And this 3, we're going to raise it to the power of 3 divided by, because there's no other product, you're not going to multiply that by anything, to the power of the reactants, which is the concentration of O3, to the power of 2. Okay, that's how you would do it. Let's say I wanted to do Kp. It's the same thing. It's just that instead of concentration, we're using pressure. So it's going to be like, you write the pressure of O2 like this, pressure with a little O2 like that, and then to the power of 3, because there's a 3 mole quantity there, and then you divide by reactants, which is the pressure of O3, and it's to the power of 2. Okay, so that's how you would set up these two equilibrium expressions. Okay, so let's do the second one now. Okay, so let's say this one, we're going to start with product, which is NOCl. So I'm going to write Kc is equal to, and then you're going to write concentration of NOCl, and we're going to raise it to the power of 2. Right? And this time we're going to divide that by the reactants. You could choose either reactant. I'm going to start with the one on the left, NO, and we raise it to the power of 2. And here we multiply. Okay, we multiply, not add. And we're going to put in Cl2. And we close the parentheses. There's a 1 here, so you don't need to put anything there. Okay, so that would be the concentration, I'm sorry, the equilibrium constant for this second reaction. I'm not going to do Kp. It's okay if you just do Kc for this one. So I want you to try the third one now and see what you get. Let me know what you get, and then check your answer. Okay, so now that you tried, you should have written Kc is equal to the product, which is AgNH32. There's a 1 in the front, so you don't need to raise it to the power of anything. And then you do these ones, so Ag plus to the power of 1, which is just that, times ammonia, and we raise it to the power of 2, because that's what's in front. So that would be the equilibrium expression for that one. Okay. So a few more concepts that you need to keep in mind are that let me move this a little bit more. Oh, I guess I can't change it. Okay, well, a few things you need to know about K. It depends only on the stoichiometry and not its mechanism. So mechanism just means reaction pathway, which is something we're going to learn about in the next unit. So don't worry about that one too much, but in the future when you're studying for your AP exams, this will make more sense because we would have already gone through Unit 7. So don't worry too much about that. K is independent of initial concentration. So it doesn't matter whether you start off with 5 molarity of product or 10 molarity of product. It doesn't matter how much concentration you have, the equilibrium constant is going to be the same. Okay, it's going to be the same. It's a constant. It's going to be the same no matter what concentration we start off with. It is also unaffected by other substances. So if they're not in the equilibrium constant, that means that they're not participating in that equilibrium reaction. And because of that, it's not going to affect K. Okay, K is not affected. So as long as the temperature doesn't change. So if the temperature doesn't change, K shouldn't change. K does vary with temperature, so that's what I just said. If you change the temperature, you will change K. The concentration will not change K, only the temperature. Because all the concentrations or all the pressures are cancelled, we don't have any units for K. And this one is a big one. Never include liquids that are pure or pure solids in the equilibrium constant. The reason why is because they don't participate in the equilibrium reaction. They're present in the same way from beginning to end, from before the reaction starts to after the reaction starts. We don't have to worry about those in the equilibrium constant. So never include those, and you're going to have many examples of that. So here's the first one. So again, keep this in mind. No pure liquids and no pure solids. So you need to memorize that. So for example, if we do that with this, these two reactions, we're going to notice that here we have a pure liquid. We don't include this. Let me write down, don't include solids or liquids. Okay. Okay. Now let's find Kc. Kc is equal to the concentration of CO, and again we don't include water because it's pure, over the concentration of CO2. However, yeah, CO2 times the concentration of H2. Okay, and for Kp, because it is asking for Kp, you just put the pressure of CO over the pressure of CO2 times the pressure of H2 there you go, pressure of H2. I know it's kind of sloppy, my bad. The second one, we have a solid. Again, we don't include the solids. And here's another solid. We don't include the solids. Don't include solids, don't include pure liquids. So if you want to put a little X next to these states of matter to remind you, do it. So Kc is equal to the concentration of CO2, and then to the power of 2 over the concentration of CO to the power of 2. And again, we don't include the solid, so this would be the Kc, and then Kp is going to equal to the pressure of CO2 to the power of 2 divided by the pressure of CO, and to the second power. Okay, so that's how you would write that. Okay, so now you guys can try. So you guys try this one. This new example right here. and see if you guys could do it. So I only want the KC for these. Okay, so go ahead and try, and then check your answers with me. Okay, so these are the answers that you should have gotten. For the first one was pretty straightforward. Just make sure you have it raised to the second power for this product, and then third power here. For this second one, you should have assumed that they're all gases, right? O2 is typically a gas, SO2 is typically a gas, SO3 is typically a gas. For this one was probably the only tricky one. Never include solids, so and because this is the only reactant, we're actually not going to have it in the denominator. We're not going to have anything in the denominator here. So this would be our equilibrium constant. So I taught you what the equilibrium constant is set up. So how is it set up? In terms of its expression, I taught you what equilibrium is and what it's not. I taught you that equilibrium constant is not dependent on the concentration, but can be changed if the temperature changes. And now I need to tell you what that means. So what does K mean? So if K is a number larger than 1 or way larger than 1, that means that the products are favored. That means that the equilibrium tends to lie to the right. Okay, so the equilibrium reaction leans to the right, you're making more product. When K is super duper small, the reactants are favored. So the equilibrium reaction lies to the left, so we're making more product. When we've been solving for K, we have been taking the products and dividing them by the reactants because we're assuming the products are on the right side. But let's say we want to find the equilibrium constant for the reverse. So we want a relationship that's actually reactants over products. And so what we do, if that's ever the case, if you ever see it on a test or on a quiz or on the AP exam, if it's asking for the K of the reverse, just do the same thing that you normally do, but take the reciprocal of K. So, and I'll show you what that means in a bit. You guys have this example, but because of the color, and it's not really too important because we have many other examples, I need you guys to get rid of this slide. But if you're curious and want to do it, then go for it. But it's not really something that we need to go over. So this is what I meant for finding the K of the reverse. So we learned already that this is an equilibrium reaction. We learned that Kc is the concentration of NO2 to the second power over N2O4, right? We learned that already. And here in this problem, it's saying that K is 0.12. And that's great. And it's temperature dependent, right? But this question is saying that what is the K value for the reverse? So if we're going from this being our reactant this time, and this being our product this time, because we're going in the other direction. So what we do is we could literally just take the reciprocal of this, 1 over 0.212, and we'd get a number, okay? And in this case, the answer will be 4.72. And I just taught you that if K is smaller than 1, here it's going to lean to the left. And because we are talking about the reverse reaction here, in chemistry, we write a little parenthesis, what do you call it? Oh my god, what is this called? What is it called? A hyphen? Is that what? No, not a hyphen. Oh my god, what is that called? Okay, I can't remember what it's called. But this symbol right here, that, you guys know it in English. Um, we, we put that there and that symbolizes, the reverse. So this, is the reverse. Okay? And because we're going in the reverse direction, it's gonna move in the opposite direction, which is the right side. And it makes sense because k is larger than 1, so it's gonna lean to the right. Okay? And we have one more example. Actually, we have two more. If you feel like you need extra practice, go ahead and do these three. Otherwise, I'm just gonna show you the answers. So if you feel like you're strong at this already, you can move on to this slide, this last slide. If not, I'm gonna show you how to do these ones. So again, pause it, try on your own, and then check your answers. So for the first one, you recognize that liquids are not part of the equilibrium constant. So you just have the concentration of CO over CO2 times H2. And for the second one, again, solids are not part of the equilibrium constant. So it's going to be CO2 and raise the coefficient to the power. And then it's just CO to the second power. And then the third one, liquids, not part of the equilibrium constant. Aqueous solutions are. Okay, and so you include those in there. And you divide that by the carbonate. So these should have been your answers. For number 17, this next problem, which is the 17th slide, now we actually start to put numbers into K. So, and the reason why I put these two problems is because it's very similar to the homework. And also you have to be very careful because here we're talking about moles, but you have to divide the moles by the liters, okay? Or if they give you grams, you have to convert it to moles and then divide by liters. So you need to get it into a form that's in concentration. So it says here, find K, tell me if it leans to the right or left. So we're gonna do the same thing we've always been doing, except this time we're gonna add numbers. So Kc is equal to the concentration of NH3. So let me start over here, because Kc is equal to the concentration of NH3 to the second power. Then you divide that by H3. H2 to the power of 3 times N2. Okay. So what is the concentration of NH3? It's 2 divided by 1. So 2 moles divided by 1 liter is just 2. And we set that to the power of 2, right? And then the concentration of H2 is 2 divided by 1, which is 2. And you multiply that by the concentration of N2, and you end up with 0.5. Okay, oops. 0.5, which means that K is smaller than 1, so it leans to the left. Okay, and for the last example, where I want you to try this one and then check your answer, we're going to write the equilibrium expression. So K is equal to the concentration of HI to the second power divided by H2 times I2, right? This is on the denominator. And now we're going to start plugging in numbers, but remember it's moles divided by 2 liters. So when you divide, for example, the concentration of HI, it's going to be 2 times 10 to the negative 2 divided by 2. So that's going to be 0.0001 or 1 times 10 to the 1, 2, 3 to the negative 4. So that is me squaring it already. So it's 2 times 10 to the negative 2 divided by 2 to the second power in your calculator will give you this, okay? Or it's going to be this divided by 2, which is just 1 times 10 to the negative 2. 1 times 10 to the negative 2 to the second power gives you this, okay? And then you divide that by H2, which is 1 times 10 to the negative 2 divided by 2, which is, again, 0.5 times 10 to the negative 2, which, you know, I have it in my calculator as 0.05. Oh boy, 0.5. And then my other value, when I divide by 2, I get 0.015. Okay. And when I solve for that, I get 1.33. And so because k is larger than 1, it's going to lean to the right. Okay, and that's what you should have gotten for this last slide.